Problem number 2. All these problems are really asking us to do is to take the exact same thing that we were just doing and apply them to some story problem situations here. In this situation, we're looking at some architecture and we're looking at a stained glass window. Apparently they're saying that the side of each small square is 5 inches. Find the perimeter of the window to the nearest tenth of an inch. So when they're asking us to find the perimeter, just understanding the problem, the perimeter, let's see here. They want that distance right there, that distance all the way around. That's what they want. So we have to add up all 4 of those sides. But they don't give us that kind of information. Pretty much the information that they give us is that the side of each small square is 5 inches. So if I were to kind of pick on, say, this square right here in the middle, draw that in there. I won't push it. I'll just shade this in. So there's that square right there. Here's the only thing that they're telling us. A side length on that square is 5 inches. That guy, highlighter right there. Okay? Terrible highlight job, but I think you know what I mean. Let me draw another little diamond shape right here. Wow, that's a great looking diamond. You know what? Mr. Cook is really lazy and he is going to cheat. Make a square. Kind of like this. And then just whoop. There we go. And so what they're trying to tell us is that this right here is 5 inches. Now, do you see the problem that we have right there? The problem that we're going to have if we're trying and find the perimeter of this stained glass window is that perimeter is only found by using the diagonals, as you can see, of those squares, right? The diagonal, 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 diagonal. I'm done saying diagonal. In other words, that guy right there, that diagonal of that square. So now is a perfect time for us to review the Pythagorean Theorem geometry, folks. So let's go ahead and put a right triangle in here. In fact, let's keep that same square, except let's not fill it in. Okay? We take a square, and we take that square, which we know all 4 sides are the same length, and now we cut it just like that. Okay? And if we do that, here's what we know. We know the side length is 5. Because it's a square, the 5 is right there. But the key to answering the perimeter question is us figuring out what the length of that hypotenuse is right there, right? So, Pythagorean Theorem. You guys have probably already figured this out by the time I even figure out even remembering how to spell Pythagorean Theorem. Okay? Wouldn't that be a squared plus b squared equals c squared, which means that a and b are always the legs, right? So there's a, there's b, there's c. So then 5 squared plus another 5 squared would be equal to c squared. 5 squared, 5 squared. Wouldn't that be? So wouldn't this give us 25 and 25, so 50 being equal to c squared? And then our finishing move with all Pythagorean theorem problems, got to take the square root, right? So I have to take the square root of that 50. Hey, think about some of the stuff we've done so far with simplifying square roots. I believe I can think of a perfect square that goes into 50. You got it. It would be 25. So wouldn't that be 5 square roots of 2? This length right here, 5 square roots of 2. So if the diagonal of that square is the 5 square roots of 2, wouldn't that make sense now that what they're coming up with here and all that little text that you're seeing right down here? Let me clear that all this riffraff. Goodbye turned square. And notice what this said right here. The length of a diagonal of a square would be s times the square root of 2. So the length of each 5-inch square would be 5 square roots of 2. So just kind of picture, well, we have a 5 square root of 2 with that guy right there. And then we have a second 5 square roots of 2 right there. And with the magic of video editing, there you have it, a whole bunch of 5 square roots of 2's. So wasn't this question asking us for the perimeter? Now, great. That little formula over there, perimeter, fantastic. I love it. 2L plus 2W, great formula, fantastic. I want you guys to be thinkers, though, but let's just be some real in-depth thinkers here. Let's just think about this for a second. Aren't we really just adding up all of these sides, and how many of these stinking 5's do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those 5's, right? So if we have 10 of those 5's, aren't those all like radicals, which we're really adding together anyway? So 5 square roots of 2 plus 5 square roots of 2, in other words, 5 square roots of 2, just simply put 10 times. Is it okay to multiply the 10 and the 5 together? You betcha it is. And so that's exactly what you're seeing right there. Okay? 50 times the square root of 2, which would be approximately 70.7. Now the reason why they do that approximate length right there is because we're dealing with a real world problem, and with real world measurements, decimals are more appropriate than radical answers. I just got a tape measure actually from my wife. She picked it up at the hardware store. Very thoughtful. And last time I checked, when I looked at that tape measure, I didn't see any square roots on them. Bummer. Yeah, just a lot of tick marks. So no square roots there. If you're doing real world measurements, let's use some decimals here. Alright, so looking at this problem over here. Stained glass window. Trickier. Wait a minute. Now it just says that it's 6. 6. Find the perimeter of the window to the nearest 1/10 of an inch. Okay. So I guess if we were to look back at this picture here, seriously, what would really just change? I guess this would change, and this would change. Mind if I just erase all of this Pythagorean, well, maybe not that. Let's erase all this Pythagorean theorem stuff, because you probably don't even really need it. Now, do you? Because I think you probably know what goes right here. If that's a 6 and that's a 6, I wonder what would go there. I'm going to leave that to you, and then I'm going to leave it to you to try and come up with that answer. Okay? So another pause job right here. Give yourselves a couple seconds to work. Okay? Great. Pause. Alright, so checking your answer. Take a look at my stained glass figure. Did you see that the correct number that we should have there, instead of 5 square roots of 2's, it would be a whole bunch of 6 square roots of 2's. So if we were trying to find that perimeter to the nearest 1/10 of an inch, how many of those 6's do we have? Well, it looks like I have, let's see here, 3 of them on top, 3 of them on the bottom. So 6, 7, 8, 9, 10. I have 10 6 square roots of 2's. So 10 6 square roots of 2's would give us 60 square roots of 2's. And we want the decimal answer there. Let's go ahead and get that. Alright, so there you have it. 60 times the square root of 2, 84 point to the nearest, how many decimal places do we want here? Let's go back here. Was it just the 10th? Yep, nearest 1/10 of an inch, so 1 decimal place, so that would be 84.9, right? That 5. We'll give that a shove, okay? So, I already forgot the number. 84.9. Alright, good. 84.9. So, the answer here would be 84.9 inches. Remember, it's dealing with perimeter, so no squares or anything like that. Just 84.9 inches. Okay, here's one thing I do want to kind of just go on a little mini rant about here, and to be cautious about, and that is rounding answers too soon to get to your exact answer. Do you notice that the only time that Mr. Cook actually rounded to get to an answer was right here at the calculator part? What I did not do is I did not do, say, 6 times the square root of 2. Like this. Get that decimal. And then all of a sudden, hey, let's just round that to the nearest 10th, and let's do 8.4. And then times 10, for example, right? If we did 8.4 times 10, look at the answer that we would get. We'd get 84, right? 84, much different than 84.85. It's not as precise, okay? Anybody here Back to the Future fans? Back to the Future fans, part 2, one of my favorite scenes is Doc Brown when he is explaining to Marty McFly what kind of reality that they were in now. And I kind of use rounding. Rounding to me kind of fits here. Imagine if we were trying to do our question, and this was our original question right here, original problem that we were doing here, and this would be our actual answer here. Because I didn't round until that very last moment, I get the most accurate answer possible. The sooner in a series of steps that you start rounding and then start using rounded answers of that rounded answer and round again and then round again, the more you round, the further off that your rounded answer is actually going to be from the actual answer. And so it's very, very important to make sure that you hold off on that rounding until the very last move. Isn't that right, Doc Brown? That's right. Couldn't have said it better myself. All right. So there's problem number 2 there for you. Let's move on to problem number 3.